Okay, so last time, we discussed how to describe a two-dimensional plane in R3. So we had two different ways to describe it. The first one was a parametric description. So parametric description was, what was that? Well, actually, the parametric description was EU plus S3 plus was something like that. So for any real numbers T and S, well, so this is what? So you can easily imagine a two-dimensional plane spanned by two vectors U and V, and then you parallelly translate that plane by vector W. Then that is going to, then this equation will give you the parametric description of a two-dimensional plane in R3. On the other hand, another description was given by this. N dot x minus u equals to this. So this another second description. This was what is this? This is a normal direction of the plane, and what was u? U was just a point that is contained in your plane, and all such x's satisfying this equation will be the point on your plane. So okay, all right. Actually, so I just want to say something more on this second description. So yeah, even if I said this description was for two-dimensional plane R3, but actually this description is even also valid for n-1 dimensional hyperplane in Rn. Why? Why is that? Because this is just a restriction. So well, and generally speaking, in n dimension, whenever you give a restriction, that will going to decrease the degree of freedom by 1, right? So this is why this guy is representing n-1 dimensional geometric space. Okay, and today, using this, we're gonna study just a little bit of applications. Distance from a point to a plane. Okay, so we consider this. So this is two-dimensional plane in R3. And yeah, this is the origin. And this is a normal vector, which is orthogonal to the plane. And I have a point, which I will call P. And this point P is considered as a point which is outside of this plane. What I want to do is this. So I want to find the length between this point to this plane. So what do I mean by that? So how would you define a length between a plane to a point? Well, that's easy. That is easy. Well, in this case, what you're going to do is just draw a perpendicular line from the point P to the plane, just like this. So this is a and the length I mean by the length of this line sigma. So this is the length between a point to a plane. So what you're supposed to, so given the plane and the point, and you're supposed to find the length of this guy. Right? So how would you find such a length? Well, for simplicity, I'm going to call this length to be L. L is the length of the line segment. Okay. How can I find this? Just like this. Well, just choose any point on in your plane, and which I will call U. So U is in the point. So U is just a point in the plane. Then I can draw a triangle from this point, and one side is from this point to the P, and the other side from this point to this point. Okay, and okay, great. And finally, I'm gonna define this angle between this normal line to this line to be the data. Okay. Then this is gonna be okay. And the length L should be P minus U times cosine theta and absolute value. Why? Why? Because this vector given by this line segment, length of this side is precisely P minus U, right? Okay, so this number is the number that you're looking for. This is the distance. Okay. Sorry. This is P minus U. Okay. And this is the normal direction, and oh, okay. Sorry. Yeah, I was just a little confused. Sorry. Okay. Suppose that this normal vector, this is a unit vector. Then this L can be also written as length of n times this, because multiplying by 1 doesn't change it, doesn't change anything. Okay, but however, if you look at this, this is the length of this guy, and this is the length of this guy, and the data over here is the length of the angle between this vector and that vector, and this one can be easily described by using the dot product. This is the n dot P minus U and absolute value, right? Okay, and you know what? Computation of the dot product is, well, just matter of high school algebra. Anyone can do this. So therefore, if you know the information about this plane, well, and in particular, if your information on your plane is given in this form, then you already know your normal direction, right? So therefore, you know this, and the coordinate of P and coordinate of U, well, this is coordinate of U, right? Is also already given there. So this is easy. So, just one more thing. So suppose, well, but usually n may not be given as a unit vector. Okay. If your n is not, what if your n is not given as a unit vector? For such cases, if n is not a unit vector. Then the idea is you can always make your vector n to be a unit vector by normalizing. Then L is going to be just 1 over absolute value of n times n. Then now this is a unit vector, right? Dot with p minus u, which is absolute value of n dot p minus u. Everything divided by length of unit vector. Okay. Okay. So this is very famous formula on the computation between the length between the point and the plane. So if you do not know this formula yet, then I guess this is really nice time to memorize it, at least by the end of the semester. Okay. And what's next? And this time we want to discuss the cross product. Cross product is basically about the multiplication of two vectors. Actually, we had such a multiplication. So we had a dot product, right? So dot product was also considered as some sort of multiplication between two vectors. But the thing was, if you take a dot product of two vectors, then that is going to give you a number, not a vector, right? But the cross product is somehow different. The cross product is a multiplication between two vectors, and however, the result is not a number, but the result is just another vector. So vector times vector is going to give you another vector. This is cross product. But there is a huge difference between the cross and the dot product because, well, dot product can be defined for any n-dimensional vectors, right? You can define the dot product between two-dimensional vectors and for three-dimensional and four-dimensional and so on. But however, the cross product is only defined for three-dimensional vectors. So, there is no such thing as a cross product between the vectors or in four dimensions. Okay. What is this? So I'm going to give you the definition first. We have such a weird definition. Well, so we have two three-dimensional vectors, v and w, in coordinate, v1, v2, v3, and w1, w2, and w3, and v cross w. So this is the cross product. So cross product of v and w is defined by this equation. Okay. Right. Well, cross product is one of the most important product for three-dimensional vectors. So, well, sorry, I'm repeating this, but you also need to memorize this if you haven't. But how would you memorize it? There is a very nice way to memorize this because this definition is very much related to the determinant of 3x3 matrices. So I'm going to show you how. So, yeah, I know this doesn't make any sense, but yeah, typically, yeah, I don't know why, but typically they use the physicist notation IJK, V1 and V2, V3, and W1, W2, and W3. So the coordinate of the first vector is on the second row, and coordinate of the second vector goes to the bottom row of this sort of matrix. But this is not exactly matrix. because these guys are just numbers, right? These six things, these six entries are numbers, but I, j, k, they represent the standard unit vectors in R3. So I is the 1, 0, and 0. This is 1, 0, 1, 0, and this is 0, 0, and 1. So each of these guys represent the standard unit vectors. Now, okay, why I'm interested in such a weird notation? Because, well, you know how to, do you remember how to compute the determinant of 3 by 3 matrix? So that goes like this. This guy times the determinant of this matrix. So I times determinant of this matrix. So which is this. And this guy, and minus the signs are alternating, times the determinant of this 2 by 2 matrix given by this. And finally, this last guy times the determinant of this 2 by 2 matrix. Then, okay, yeah. For those of you, such a notation is not that familiar with. Expanding this, V2, V3 minus V3, V2, sorry, W2, minus V1, W3, minus V3, sorry, W1, and finally, V1, W2 minus V2, W1. So if you remember the computation of the determinant of 3 by 3 matrix and 2 by 2 matrix, then you can easily derive this formula from this notation. Okay. So, yeah. Well, yeah. If I'm being truly honest, then yeah, I still do not memorize this formula. So what I remember is this equation is something to do with 3 by 3 matrix. So this is for now, even for now, yeah. This is how I memorize this. Okay. All right. Since this, so this is the definition of the cross product, and since the cross product is very much something to do with the determinant, so cross products somehow inherit the properties of the 3 by 3 matrix. Well, first, suppose that we have 3 vectors and a number. Then this cross product is also respecting the distribution law. Is B, well, yeah, which I will not prove. But this is considered somehow obvious. And number 2, so this also respecting the scalar multiplication is C times V dot W, and V cross C W is C times V cross W. Last but not least, sorry. this is what. So first, you're supposed to take a cross product of these two vectors. Then this inside the inside of this parenthesis, you have another three-dimensional vector, and this three-dimensional vector is being taken dot product with another three-dimensional vector. So this is basically dot product between two three-dimensional vectors. So the resulting thing would be not a vector. This is number. This guy is called the so-called the triple product of three vectors u, v, and w. So this is sometimes called the triple product. And I claim that this is the determinant of u, v, and w. Do you remember this notation? So this is what? So this is determinant of 3 by 3 matrix whose first law is the component of the vector u, and second law is the component of the vector v, and the last law is the component of vector w. Why is that? Because v cross w was given like this, then since you're taking the dot product with another vector u, so therefore, because u dot v, this triple product is u1, u2, u3 dot product with this guy. And this is what. So if you take a dot product, then you multiply this guy by this, and you multiply this guy by that, and you multiply this guy by this. And this is actually u1, u2, u3, v1, v2, v3, and w1, w2, and w3. And this is precisely the determinant of vector u, v, and w. So this is called the triple. Great. Great. Oh, this last identity is also true for all three vectors, three-dimensional vectors u, v, and w. And this is called the Jacobi identity. So, okay. How was I able to memorize this formula, this identity? Well, you have three terms on your left, and this appearance of the vector u, v, w is in cyclic order. U, v, w, and v, w, and w, and v. So they are given in this cyclic order. And okay, and this is not just a weirdly looking random identity. This actually tells us very interesting thing, nature that appears in the cross product. That is, the cross product is not associative. 한국말로 결합법칙에 성립하지 않아. 그러니까 여러분들이 수학을 배우면 되게 많은 엘지브라를 배우잖아요. 특히 곱셈 같은 거는 우리가 곱셈은 대부분의 우리가 심지어 매트릭스 멀티플리케이션도 우리가 어소시에이티브템 성립하죠. 결합법칙에 성립하죠. 그렇죠? 그런데 크로스 프로덕트는 어소시에이티브가 성립하지 않는 첫 번째 예시가 돼요. 혹시 그거 보이시나요? Because is V. This is minus V. 이거죠? 근데 이거는 okay. Sorry, I forgot to just mention just one thing. Sorry. Before I should mention this theorem before I even mention the associativity of the first part. Okay, sorry. Okay, let me cover this theorem first. This theorem says three different things. So V cross W is orthogonal to the V and to W at the same time. So what does it mean? So you have two three-dimensional vectors. This is say that this is V and this is W, and V cross W is gonna be orthogonal to those two vectors at the same time, right? So in other words, I can rephrase like this. Just try to imagine a two-dimensional plane that is containing the vector V and W at the same time. Then V cross W is going to be the normal vector of the plane. Right? This is the claim of the letter A. And letter B. We have seen this before. So what was this? So except for this 1/6 vector, this U dot V cross W this turns out to be the triple product of U, V, and W. Then this triple product divided by 6 is going to be the volume of the ordered tetrahedron, signed volume of the ordered tetrahedron that is generated by vertices U0, U, V, and W. And finally, V cross W is W cross V is minus of V cross W. So in other words, the cross product fails to be commutative. Actually, in fact, this is what you call the anti-commutative. So if you change the order of the cross product, then the sign also changes. So you have to be really careful when you try to change the signs order of the cross product. All right, so I'm going to give you the proof of this. A. This is what? This is a determinant of V, V, and W. And since these vectors, V, V, W, and I am pretty sure that this number should be 0. Why? Because this determinant turns out to be, what this determinant was, a signed volume of a parallel pipes generated by those three vectors, right? But in this case, these two vectors are the same thing. So V and another V, the same V with W. Therefore, parallel pipe generated by these three vectors must have the 0 volume. Why? Because that parallel pipe is actually contained in the plane generated by vector V and W, right? So therefore, this guy should be 0. And likewise, so this is W, V, and W. By same reason, this guy should be 0. So therefore, these two dot products, they all equal to 0. Therefore, so we prove this plane. So V cross W is both orthogonal to the V and W. Letter B. Mm, uh, okay, all right. So I should draw a picture. This is the origin, and say this is vector u. And I have another vector v, and I have another vector w. And let me try to consider the parallel pipe generated by these three vectors. That is going to be and okay, great. So this is, well, yeah, my picture is not perfect, but you know, this is the parallel pipe generated by these three vectors, u, v, and w, right? Okay. And what is the volume of this guy? So volume of this guy turns out to be just triple product of these three vectors, right? And this theorem claims that it's about the tetrahedron with vertices, the origin u, v, and u, v, and w, right? So in this theorem, so this theorem is about this tetrahedron, right? This yellow guy. So the letter B is about the volume of this tetrahedron. So comparing the volume of this tetrahedron and the volume of the parallel pipe, I believe the volume of this tetrahedron is precisely 1/6 times the volume of the parallel, right? So that proves the claim letter B. So, well, yeah, precisely speaking, so yeah, it's going to be the volume of the tetrahedron. And finally, I am supposed to show this. Why? Why the cross product? Why is the cross product anti-commutative? Oh, that is because the nature of the determinant. Yeah, I am trying to prove. But do you remember the notion of the signed volume of the parallel pipe? Well, remember U, V, W. So this was defined to be so-called the signed volume of the parallel pipe generated by U, V, W, right? So okay, hey, what do I mean by volume is signed? Volume has a sign. So that means if these three vectors, if they are given in the positive orientation, then this volume is going to be the plus. We'll have the plus sign. However, if these three vectors, if they are given in negative orientation, then this number would be negative of the volume, right? So this guy, actually, well, precisely speaking, so sign of this number is very sensitive about the order of these three vectors. Okay. All right. So therefore, the cross product is actually given by was it? Yeah, V and W. This is actually cross product borrows its computation from the determinant. Therefore, this guy should be also very sensitive. The sign of this guy should be also very sensitive to the order of these three things. But this first law is always fixed. Therefore, if you interchange the order of these two vectors, then that will probably change the sign of your resulting vector. Right? That is why this cross product is anti-commutative. Great. Then now I can finally say why this Jacobi identity is about the non-associativity of the cross product. Because so can you see the Jacobi identity over there? Yeah. So U cross V W is minus of V cross W times cross U minus W cross U and another cross with V. So this is the Jacobi identity. But if I change the order of this guy, then this is going to be plus U cross V cross W, right? So this is this is my version of the Jacobi identity. And you know what? So if the cross product were associative, then there should be no such term over here. This guy should be 0, right? But in generally speaking, this last term may not be 0, right? That means cross product is not associative. So this is why I'm claiming that the Jacobi identity is about the non-associativity of the cross product. Okay, all right, good. Oh, sorry, I would like to add just one more thing about this theorem. Okay, let me go back to the statement A. So you have two vectors, V and W, V and W. Then it says V cross W is pointing towards the direction which is normal to the plane generated by V and W. But actually, you have two such directions, this or that, right? But then which direction? The direction is also given by the right-hand rule. So I mean, the thing is, I would say this is first vector, and this is second vector. And raise your right hand, and say that this is the direction, and this is the direction of your first vector, and curl your right hands towards the second vector. Then the direction that your sum is pointing is going to be the direction of V cross W. Well, yeah, I should better draw a picture of this. Yeah, I'm really bad at drawing pictures, but so is it look like the right hand? Yeah, please. I don't know. Yeah. So this is the right hand. Say that this is the right hand. Then say that this is the direction of the first vector. And this is the direction of the second vector. And if you curl your right hands towards the second vector, then the direction that your thumb is pointing is going to be the direction of V cross W. Okay, so quick question. You know the standard unit vectors, I, J, and K, right? what is I cross J? Plus K. Plus or yeah, plus should be plus K. But J cross I is going to be minus of K. Good. Okay, so far we have discussed so many properties on the cross product. And so given two three-dimensional vectors, we now know the direction of the V cross W. But there's one more thing to left. So we still do not know the magnitude of the vector V cross W, right? We know the direction of the V cross W, but we do not know the magnitude. And this last proposition is about the magnitude of the cross product. The proposition is the magnitude of the cross product of two vectors is the length of V times the length of W times sine of theta. Here, theta is the angle between theta is always from 0 to pi, is the angle between two vectors, V and W. This is the magnitude. This one, the right-hand side, or the right-hand side of the equation looks very much like the magnitude of the dot product. Magnitude V dot W equals to the magnitude of V times magnitude of W times cosine theta. But this time, this is not the cosine changes the sign, but they are almost identical to each other, right? Okay. Why? Why is that? Suppose that I have, let me introduce another vector. And this is a unit vector, which is parallel to which is pointing the same direction as the V cross W. Then I want to consider this triple product, V cross W. Then this is going to be the volume of the parallel pipe. Which parallel pipe? If this is vector V, and if this is vector W, and because by the right-hand law, so this direction would be the V cross W, right? But this U, even though U is pointing the same direction as V cross W, but it says this is a unit vector, right? So therefore, this blue vector would be my U, right? And this parallel pipe that we are talking about is this guy. Right. This is the parallel pipe given in this phrase. All right. What is this? What is the volume of this guy? Well, this is actually not parallel. Well, this is a parallel pipe, But this is a right parallel pipe. So this is not slanted, just a right parallel pipe. So the volume of this guy would be the area of the base times height of this parallel pipe. But height is just one, length is one, right? So therefore, I say the volume of this parallel pipe is the same as length of the area of the base. So area of the base. What is the area of the base? Area of the parallelogram spanned by V and W. But we have two vectors. This is V and this is W. And this area of the parallelogram is also known as V, the length of V times length of W times sine theta. Okay. Do I need to justify this? No. You already know this formula. Okay. And on the other hand, U cross V this is because of the dot product, the theorem from the dot product. This is length of U times length of V cross W times cosine of the angle between these two vectors. But here I said U and V cross W, they are pointing the same direction. So therefore, this angle should be zero, right? And also we are assuming that U is a unit vector. So this is V cross W. Oh, I guess we already proved the theorem. See? So this guy on the one hand equals to this, and on the other hand, this guy equals to that. So they are the same. Okay. So this is all about the cross product. So now we know cross product. So for any given three-dimensional vectors, the cross of V times V cross W is gonna be an angle where it's a direction, it's another vector, which is orthogonal to the V and W at the same time, and whose direction can be determined by using the right-hand rule, and whose length is also determined by this last proposition. Good. Okay, so we are done about the chapter 1, and now we are moving to the chapter 2. About functions. Before I introduce the functions, but let us just settle the basic terminologies. 여러분 혹시 surjection, bijection, injection 아니면 그런 거 혹시 아세요? 모르세요? 오케이. 네, 제가 할게요. Okay, forget. Yeah. Many times we use such a notation when we are describing a function. Well, as a set theory, this is the domain. This is what we call domain or 정의요. And why this is what we call the codomain, or in Korean, the 공영. Right? Yeah. So this is domain. This is codomain. And well, we usually the lowercase letters represent the element in the domain, but if I put on the uppercase letter, then this one should be understood as a set, a subset of the codomain. So what is this? So this is fx such that so what is this? This is not just an element, but this is a subset of Y, right? Collection of all elements that is being hit by at least one element from the domain, right? So this is what, so from now on, we're going to denote f of large X. And this guy is usually written as range of f or the image of f. range가 한국말로 뭐라고 하죠? 치역이라고 하죠, 그렇죠? So usually range is not necessarily the same as the codomain, but sometimes your range can be exactly precisely same as the codomain of your function. In that case, we say the function is surjective or surjection. If f, the image is the same as y, then f is called surjection or surjective function or onto function. All these terminologies, they are widely used in mathematics. So yeah, you should better know this. And if fx1 is fx2 implies x1 is the same as x2, then f is called injection. Or 1-to-1 function. So here I'm introducing the surjection and injection. So what do I mean by that? Okay, so that means suppose that if two elements in the domain have the same image, and if this implies x1 equals x2. So in other words, every element in your domain, every element in your codomain is being hit by elements from your domain at most once. Right? So there is no such a thing. So there is no such a thing as being hit twice. So this is what we call the injection. And if your function is injection and surjection at the same time, then we say that is bijection. Sorry. So if your function is bijection, then every element from your domain and every element in your codomain they have the one-to-one correspondence. So in other words, intuitively say the number of elements in the domain is the same as the number of elements in your codomain. Or using more involved terminologies, we say the cardinality of the domain and codomain are the same. Well, I mean, so this is, well, these are some basic terminologies. Well, I guess we're going to use these terminologies a lot for the rest of the semester. Okay, that is that. And but in our, for the purpose of our course, we will be mainly interested in the functions whose domain and codomains are the subset of the real, sorry, domain and codomains are a subset of n or m-dimensional vector spaces. So these guys are, so from now on, we will be mainly interested in the function whose domain is a subset of Rn and whose codomain is Rm. Okay, so what does it mean? If you have such a function f, then if you plug in any n-dimensional vectors into your function f, then that you're going to produce m-dimensional vector, right? So in component, x is an n-dimensional vector. So f of x is going to be a vector in Rm, and typically every vector in Rm can be written in terms of coordinate. So this guy would have n coordinate, n components, right? So, and each of these components from small f1 to small fm of x, all these guys are should be considered as a function from Rn to R, right? So, well, in particular, if your function has a domain in R1, then we say that it's a real values function. But this is not, well, this is a vector values function. But so in other words, I say every vector values function whose codomain is Rm must have m component functions, and each of these component functions is a real values function. Right? You must be able to find all these component functions. Right. So this is one very important observation towards the multivariable calculus. So every vector value function must have the component functions, and all these component functions are they are all real values functions. Okay. And what do I mean by a function is constant? Constant function is, so suppose that I have a function from Rn to Rn, and no matter which vector you plug in for your function, but if the resulting vector is all the same thing, then we say that it's constant function. And the most important kind of function is the linear function. So do you remember the definition of the linear function? Yeah. If your function from Rn to Rm is respecting the scalar multiplication and vector addition, then we say the function is the linear function. Right. Okay. And you also need to remember every linear function can be represented by a matrix, right? Well, 퀴즈 한번 내볼게요. 여러분, Rn에서 Rm으로 가는 리니어 펑션은 몇 바이 몇 매트릭스로 표현될 수 있을까요? 그렇죠. n by n 매트릭스로 표현할 수 있어야겠죠. 그렇죠. 그렇죠? 여러분들 약간 하도 오래돼서 약간 기억이 안 나시는 분도 있을 것 같은데. Okay, all right. So just to remind your memory, 2x minus 3y x 5y minus 7. Is it linear or not? Linear? Yeah, no, not linear. Why? I remember if your component function is a degree one polynomial, then well, it was linear, right? No, actually that is not true. So in order to be linear, then you should not have this constant number. Constant. Every component should be linear. But so that means if I remove this -7 from the last component, then this is a linear function, right? Okay. All right. Then let us try to figure out its matrix representation. 여러분들 제가 하면은 여러분들도 속으로 한번 생각해 보세요. 이거 matrix representation 어떻게 될까? 한번 생각해 보세요. Then this guy can be represented by since is well, it takes two-dimensional vectors, and this guy is going to return you three-dimensional vector. So therefore, this is vector from R2 to R3. So therefore its matrix representation must be 3 by 2 matrix, and the first column is 2, 1, 0. Hey, how did I get these numbers? That is because if you plug in, so the entries in the first column is obtained by just plugging in the standard unit vectors, the first standard unit vector. Well, in other words, if you plug in 1, 0 into x, y, then you're going to get 2, 1, and 0. That is why I'm getting these guys here. And if you plug in the second standard unit vectors here, I mean, x, y equals to 0 and 1, then you're going to get -3 and 0 and 5. So this matrix should be understood as the matrix representation of this linear function. Okay? 그렇죠? 그런 게 있었죠? Okay. The Professor Lux and Perot, so they are repeating the same theorem. So it goes like this. Every function, linear function L from Rn to Rm can be written in matrix such as this. So what is this? Since it's Rn to Rm, so I have m many rows and I have n columns. So this one is being represented by n by n matrix, just like this. And we say C is the matrix of L or the matrix that represents L. 여러분 여기서 제가 잠깐만 퀴즈를 더 하는데 여러분 그러면은 아까 방금 전에 제가 드린 말씀 중에 모든 Rn에서 Rm으로 가는 함수 어떤 함수가 리니어라고 하더라도 그 함수 자체는 Rn에서 Rm으로 가는 친구잖아요. 그렇죠? 그렇죠? 그러면은 이 리니어 펑션 L이라는 친구도 보면은 n개의 컴포넌트 펑션을 가지고 있다라고 볼 수 있겠죠. 그렇죠? 그러면 각각의 컴포넌트 펑션들은 어떤 모양을 가지고 있어요? 그거 되게 생각보다 되게 쉬워요. 어떻게 생각하면 되냐면요. 이게 그러니까 이 친구 내적 이 친구가 첫 번째 컴포넌트가 되는 거죠. 그치? 그다음에 이 친구 곱하기 내적 곱하기 이 친구가 두 번째 컴포넌트가 되는 거기 때문에 이걸 이렇게 볼 수 있어요. 여기 각각의 라인 바이 라인을 우리가 어떤 행벡터라고 볼 수가 있다. 이걸 제가 뭐 편의상 제가 이거를 뭐 C1이라고 하고 이걸 C2라고 하고 땡땡땡 이걸 CM이라고 할게요. 그러면은 어떻게 쓸 수 있냐면은 가끔씩 이렇게 쓰게 돼요. 모든 리니어 펑션은 다음과 같이 나타낼 수가 있어요. C1 내적 X, C2 내적 X, CM 내적 X 이런 식으로 표현할 수가 있겠죠. 그렇죠? 모든 리니어 펑션은 다음과 같은 형태, 이런 형태의 컴포넌트 펑션을 가지고 있어야만 하고요. 반대로 이런 형태의 컴포넌트 펑션을 가지고 있는 친구는 언제나 이런 매트릭스 레퍼런스를 가지고 있을 테니까 리니어라고 볼 수가 있을 거 아니에요. 그렇죠? 그렇죠? 그래, 대단한 거 아닌데 그냥 제가 대단한 척 이제 갑자기 한국말로 얘기하니까. 음, 이거 진도가 너무 늦게 나가서 큰일이다 진짜. 네. 이건 제가 배가 아파서 화장실에 가야 될 것 같아요. 미안합니다. 오늘 조금만 일찍 끝내도 되겠죠? 죄송해요. 다음 시간에 5분만 더 많이 할게요. 네. 미안합니다. 오늘 여기까지 하도록 하겠습니다. 수고하셨어요. 네. 네. 특히 여러분